Okay, I got about 20 seconds into this and the memory card filled up. I was a little careless. Okay, so what we want to do is we want to take the same points we had before for the exponential function and fit a vertically stretched power function to the 2 points. The power function is y equals ax to the p. The general power function is a y equals x to the p function, like x squared or x cubed or x to the -1 or x to the -2, all basic functions for this course. And then we vertically stretch it by factor a. Now p could be any power. It's not confined to 2 or 3 or -1 or -2. It could be any power at all. So to fit these 2 points to the model, we plug the coordinates into the form y equals ax to the p. Well, that's easily done. 1 equals a times 3 to the p, 4 equals a times 7 to the p. When y is 1, x is 3, that's what this says. Or when x is 3, y is 1, x is 3, y is 1. When x is 7, y is 4. So when x is 7, y is 4. We divide the second equation by the first. We chose to do it this way. We could do the other way. The steps are almost identical up to a point to the steps that we use if we're doing an exponential function. So we divide the second equation by the first. I've got a couple of dots here. That indicates that I'm not filling in all the steps. I really think we need to separate out those a's. So we have a over a times 7 to the p over 3 to the p. So we'll understand why the a's can be removed. I hate to use the word cancel because people don't ever remember the rules and do it wrong. Yep. As a result, it's not good for their grades or anything else. Okay, so anyhow, but I skipped that step. We then get 4 equals 7 to the p over 3 to the p. And of course, 7 to the p over 3 to the p is 7/3 to the p. Okay, so there we have it. So now we have this, which I've just repeated. How do we solve this for p? We only have one variable here. How do we solve that for p? Well, there's a rule. Now I wrote down the rule that a equals b to the p is equivalent to log base 2 of a equals p. An example of that is y equals 2 to the x. So a would be y, b would be 2, is equivalent to log base 2 of x equals y. And that just goes back to your tables. For y equals 2 to the x, you get your columns. Column for x and a column for y. And you reverse your columns and you get y equals log base 2 of x. And that would then have your x and your y columns reversed. So we reverse these columns to get this. And we then see that the graph of the exponential function is equivalent to the graph of the logarithmic function. So these tiny sketches here should invoke what you knew a couple of months ago about these functions, what we did very early in the course. Okay, so anyhow, it's just this, applied to any power p, not just the power 2, or any base b, not just base 2. Applying this rule, and you're not going to be expected to do this anytime real soon, but coming up in another couple of weeks. we see that this, applying this rule, is equivalent to saying p is log base 7/3 of 4. Of course, that's a log of 4 divided by the log of 7/3. Now, another thing that I'll just mention, we could use log to any power, or log to any base. The log is log base 10. There's a natural log, ln. Your calculator has both of those. And there's also log to base 2. Your calculator doesn't have base 2 log, but I can figure this out using base 2 logs. Since 2 to the second equals 4, the base 2 log of 4 is 2. So I know that I'm doing base 2 logs, the numerator would be 4. The denominator is just a little over 2. Base 2 log of 2, if you just make the table, you'll see, is 1. So log base 2 of 7/3 is just a little bigger than 1. So I'm guessing that we're going to have to divide 2 by a number a little bigger than 1, which is going to give us a number a little less than 2, so I just guessed 1.7, maybe 1.8. Don't think it'll be as much as 1.9, because 7/3 is a bit more than 1. Okay, so that's how I approximated this. So take that for what it's worth, and it's not worth much. The calculator would give you a much better approximation. And you have log buttons on your calculator. So you could verify and see how close I got if you want to in just a few seconds. You just do log of 4, and you divide that by the log of the quantity 7/3. You should get something close to 1.7, maybe 1.8, in that range. Okay, anyhow, you plug that number then into the first equation. Okay, see, we've got a value of p. We can plug that into either equation. Well, I've chosen to plug it into the first equation. Actually, might have been better off plugging it into the second, but I know what the square root of 3 is and stuff, so I plug into the first. Okay, so plugged into the first equation, well, the only difference between this and this is I've replaced p by its value 1.7, or the value that I approximated. Okay, then we solve and divide both sides by 3 to the 1.7. We get a equals 1 over 3 to the 1.7. So I know what 3 to the 1.5 is. It's 3 times 1.732. It's about 5.2. So if this was 1.5, I'd have 1 over 5.2. If this was 3 to the second power, I'd have 1 over 9, because 3 to the second is 9. 1.7 is closer to 5.2 than it is to 1.5 than it is to 2. It's concave down. I estimated 1/7, and now my reasoning tells me I probably should have made that a little less than 1/7. We're just going to go with that. Okay? Don't think it'll be as small as 1/6. Okay, so a is then approximately 1/7. Our function is y equals ax to the p. A is about 1/7. P is about 1.7. So here's my a, here's my p. Now, over here I say that y equals 1/7 x to the 1.7 is our approximate model for these 2 points. Okay, this point and this point. We also know that if x is 0, any positive power of 0 is 0, and any negative power of 0 would be undefined. So this is positive power, so 0 to the 1.7 is 0. So when x is 0, y is 0. That means the graph goes through the origin, just like the graphs of the basic squaring function, the basic cubing function. So I'm saying the graph maybe looks something like this, probably a little flatter down here, but you get the idea. Okay? So there's an approximate model for a power function between these 2 points.